All right, thank you very much. Then, without further ado, Nick Huggett, who will be talking about quantum gravity in the laboratory. Please, Nick.
Hi, yeah, thanks everybody. So do jump in and ask questions along the way if you have them. I put up, so there, I don't know if you can see it, the slides are available online if you want to download them now sort of quickly and then have them in front of you as I'm presenting. Although actually this set of slides is the ones from when I gave the talk last time, so they're very, very similar. There are a couple of little changes that I put in there. It's 3Z4 QC capital B capital J if you're having trouble reading it. Okay, well, I'm going to try and put on some entertainment in this room as it is in the picture here. But that's what's usually going on here. Okay, so let's try that. All right, so there is the question mark here, and I guess that's the sort of substance of the talk. What I'm going to talk about is some recent proposals for experiments, you know, that optimistically might be carried out in the next few years, decade or so, to actually test or produce quantum gravity effects in the laboratory. And so talk about what those experiments are, some of the interpretation of these experiments, and then actually at some sort of philosophy of science meta level talk about how to understand some disagreements that have come up amongst people talking about these experiments. So this work, as you can see, is partly with Mike over there and also equally with Niels Linnemann. And as it's a collaboration. I think we went in with some different sort of intuitions about this. The paper now represents statements that we all agree to. When I first gave the talk, I had to give fairly strong warnings that the things I would be saying might not be agreed to by Mike and Niels. I think I should still give that warning, but I think we're in much more kind of agreement here. But still, you can't sort of necessarily pin everything and every word I'm going to say today on those two as well. Okay. So I didn't rewrite although I knew David was giving the talk, I didn't rewrite the first slide in the light of his talk. But it does already, it already reflected in some ways what he was talking about. So it's customary to start talks about quantum gravity and about the experimental side or phenomenological side of quantum gravity by pointing out. I don't know what it is because it's showing here. This is flashing yellow for some reason. Now I've turned it off. I'm going to keep talking while you keep pressing that button.
Okay.
I think you can probably, the slides add something to it, but not everything. Right, so there's a customary way of talking about this that sort of points out how incredibly hard it is to test quantum gravity, and how you'd have to build a collider from here to the sun to kind of reach the Planck energies, and how terribly difficult that is. So that is advancing over there. But of course, we know from today that that's a kind of naive way of thinking about things, and it's really, pretty kind of inaccurate if you really think about what's going on. So trivially, the most simple level, the goal of a theory of quantum gravity is going to be to recover ordinary quantum mechanics, quantum field theory, general relativity, and insofar as we have faith that theories of quantum gravity just recover those limits, then they have plenty of predictions. Of course, what's harder is to talk about novel predictions. But even there, as David's explained, the way I would put it is, if you think about the theory, if by quantum gravity you mean the effective field theory limit of some theory of quantum gravity, effective field theory applied to general relativity, there's a well-developed theory, and as David's explained really nicely, there are plenty of applications of that are in fact novel predictions, and so that certainly exists as well. And in particular, I think what are the most sort of interesting applications, or the first class of really interesting applications, are the ones that involve semi-classical gravity. So you have a sort of mean field approach to. Goodness me, okay, it's really rebooting. So you have, so you basically have that. You have a system where you have quantum matter, but you have to take its expectation value and couple that to the metric field or the Einstein tensor. Okay, so where are we? Good. So that's the one I want. There really are tested applications and most of the examples, I think a lot of the examples that David was talking about are here, and there really are tested sort of novel applications of this. David was kind enough not to sort of name names for the sinners who had said this, but I will note that the introduction to our book starts with just such an application by means of, it's actually about, calculations done to see whether, I think the Brookhaven collider was going to produce black holes and sort of destroy the world. And that, that's another kind of example of this kind of calculation, sort of broadly speaking. I think pushing, so that's one regime, where tests exist, as we talked about this morning. Would sort of also emphasize the other example that he gave, to do with the sort of how the inflaton field can give rise in the early universe can give rise to observed fluctuations in the CMB, and that is crucially different because it's outside the in the standard way of doing that calculation, the Weinberg textbook way of doing it. It's exactly right. You do actually have to not take a kind of mean field approach. You do actually sum over, you have a path integral summing over all different states of the metric field. So you are thinking about superpositions of geometry in that case. Still, so that's a really key case, and it's relevant to the kind of example I'm going to talk about. But it's quite theory dependent. I mean, it does depend on on a standard theory of inflation, widely accepted, not super kind of controversial, though somewhat controversial in some quarters. I'm going to talk about an example. The example I'm going to talk about, the experiments people are thinking about, also can be thought of as requiring a superposition of space-time geometries. So sort of full-on, beyond, and you'll see this in more detail, beyond semi-classical gravity in a kind of crucial sense. Sorry, I have this one ahead, so I meant to put that up already. But I would say less dependent on sort of theory on sort of background theoretical assumptions, though, as you'll see, still dependent on some theoretical assumptions. So, for instance, you don't have to accept the standard theory of inflation for the kind of examples I have in mind. So, this is sort of the question. We want to see, it's also not experimental, it's observational. So, what's being proposed is essentially an experiment, something that could be done in the laboratory, or perhaps a very big laboratory in a field somewhere, something like that. It depends how it would be realized, to actually see the quantum nature of gravity. Well, what would that sort of look like? In these cases, it's in many ways useful to sort of appeal to the electromagnetic analogy and sort of think about how you would, how do we see the quantum nature of electromagnetism? I won't keep drawing the analogy to electromagnetism, but if you have it in the back of your mind, you'll see a number of the things that I say. It can be helpful to think, what would that look like in electromagnetism? Okay, but the first thing you think of course, what you learned probably in high school, well, the photoelectric effect, right? That's the kind of how we see the quantum nature of electromagnetism. But, bad news in the gravitational case. If you think about a hydrogen atom, what's the energy gap? What's the electromagnetic energy gap between the N1 and N2 levels? It's about 10 electron volts. But the gravitational potential energy difference, so if you're imagining emitting a graviton from, could you see a graviton emitted, if an electron a hydrogen electron jumped between energy levels? Well, it's 10 to the minus 38 electron volts, so it's like nowhere near anything anyone's ever going to see. So people think about other ways that you might try to observe the quantum nature of gravity, what the other things that might mean. So one thing you might think of was, suppose I have a material system in a quantum superposition, and it interacts with the gravitational field, and so becomes entangled with individual gravitons, and so it's no longer in a coherent superposition. Now it behaves like a mixture. So people think about experiments like that. Still extremely hard, but much more kind of promising, far more sort of feasible than this. But the kind of experiments that I'm going to be discussing, or I guess I already am discussing, involve a different kind of technique, which is really kind of quite cool and I think gripping. The question is, what exactly do they show? So the basic idea of the system is to have have mass around the scale, around the Planck mass, which is about, I think, it's about the mass of a flea egg. So it's actually a kind of human-sized kind of mass. On the one hand, you want to, it's still very small. So over here we have this sort of experimental ability to observe gravitational fields and gravitational effects. But in recent years, people have been able to measure gravitational fields of increasingly small bodies. So we're coming down from sort of heavy, right, to scales where we can measure gravitational fields. On the other hand, we want to keep it in a quantum superposition. We need small things, but at the same time, people have been performing experiments to keep larger and larger bodies in coherent quantum states. And I guess I have to put this down. And the idea is that these two regimes will come together. We can have something smaller, heavy enough that its gravitational field can be detected, or its gravitational effects can be detected, but small enough, but that's getting higher and higher, that it can be kept in a quantum coherent state, so that we can measure the gravitational effects of objects in quantum coherent states. We'll call these gravcats. It's not a very pretty name, I think, but gravitational Schrodinger's cats. These kind of tiny little bodies would be like little Schrodinger cats. So that's the basic idea. Okay, so that's all by introduction, and I'll go very quickly through the outline. First of all, I'll talk about the physics. So I'll give you a kind of naive account of how this experiment is supposed to work, so you can get the basic idea. What I'm going to... Oh, this is not good. Okay, it's just the boring outline. All of you who didn't download my slides are now regretting it, I guess. Then the one crucial point is that this experiment is actually incompatible with semi-classical gravity. So I think one reason people are excited about it is, I understand David's arguments about the Page and Geilker experiment, but a lot of people feel this would be like a much more definitive kind of experiment to rule out semi-classical gravity. So I'll talk about that. Did you just give up?
No, I haven't been.
Oh, that's not good. Okay. But there are two ways of understanding what's happening in the experiment. Well, maybe more, but I'm going to focus on two ways of actually interpreting what's happening in the experiment. And these lead to a disagreement about whether, in what sense, you're seeing the quantum nature of gravity. So one is the Newtonian way of modeling things. Another I'll call the tripartite way of modeling things. Once the physics is set up, I almost feel like I should just point the computer at. But, yeah. Okay, I will talk about the interpretation. So really, face the issue of whether this experiment would produce quantum gravity. We can edit all that out, right?
Yes.
All right, so let me describe the experiment. I'm going to give you the naive view, the sort of a naive account of the experiment, and then we'll fill in the detail, fill in sort of more details in 2 ways. All right, so you've got to imagine you have 2 of these things, these gravcats, and so one of the original papers suggested that these might be 10 to the minus 2, 1/100th of a microgram each, which I think is either 100 times the Planck mass or 100th of the Planck mass. I kind of can't remember which. I think it's 100 times, but it might be the other way around. Okay, so they're going to be in a superposition. The state's going to be separable, but each of them's in a superposition, a spatial superposition. So if you can see that, so okay, I've got the terms on the left of the tensor product are always going to refer to gravcat 1. So that's in a superposition of a left packet and a right packet around a position minus d. The terms on the right of the tensor product are always going to refer to the second gravcat. I didn't put 1s and 2s in just to keep the notation cleaner. Okay, and so that's in a superposition of left and right around a point plus d. So, right. I mean, I'll expand out the superposition, but it's still a perfectly separable state. So, but now think about, I've got my equation, so over here we have 4 terms, right? But the first term corresponds to 2 gravcats that are both in the left position, the second term to a gravcat, the first gravcat being over here in its left position, and the second gravcat being over here in its right position, so much further apart than when they're both in the left position, and in particular much further apart than the third term, which corresponds to the gravcat 1 being on the right and gravcat 2 being on the left. So each of those terms in the superposition, as I've just written it, corresponds to a pair of gravcats, but they're always at different distances. So because they're different distances from each other, in each of those terms, they'll be sitting in different gravitational potentials. And so over time, those different potentials will lead to different phase factors in the usual quantum mechanical way. So I've written in the terms here. Now if we solve the time-dependent Schrödinger equation, you'll see each of the terms picks up a phase that depends on the distance apart, because it depends on the different potentials that you get in those different situations. And so, because of these phase shifts, that is now an entangled state. This is not separable any longer. So this is just basic quantum mechanics. So we have a gravitational interaction. It takes a pair of gravcats that are not entangled to a pair of gravcats that are entangled. So to fill out the experiment a little bit more, you imagine sort of maybe the gravcat, that these chips of diamond are charged and have spin. Put them through a Stern-Gerlach machine each, so that they're each separated. Let them sit in their mutual potential. Okay, it has to be the case that there's no other forces involved. I mean, they're neutral. There's no van der Waals forces. Effectively, the only forces involved are their gravitational attraction. They sit there for a while, then you bring them back, then you put them back through the other way through the Stern-Gerlach apparatus to recombine them. But now you're going to, because of the spins, you're going to have spin entanglement. You do a measurement afterwards to check for spin correlations. And the way you would tell that they were entangled would be that you would see violations of Bell inequalities. So that's the kind of conceptual and indeed that sort of outline of some experimental protocol to actually measure this, going from unentangled to entangled system. Okay? And the claim is, from the various people who kind of proposed this, if you see such gravitationally induced entanglement, so this sort of experiment has had various different names that you might see in the literature, but some of it is sort of heading towards calling these GIE experiments, gravitationally induced entanglement, or things similar. The claim is that that would witness, or be some kind of indirect observation, one might try to think about exactly how to fill that out, of the quantum nature of gravity. And in particular, there were these two papers, pretty much simultaneously, but definitely independently in 2017, by Berza and a group of other people, and by Marletto and Vedral, that basically gave similar kind of protocols for doing an experiment like this, and said this had the same kind of conclusion. The CNR 19 paper is Christodoulou and Ravelli, and I will come back to that, but they also say this. But I hope, and I'm really encouraged in this hope by the fact your hand just went up there, that there seems to be nothing very quantum going on here at all. Is that what you were going to say?
I'd like to ask the question, how feasible do you think it is to implement the first initial state? To have the state in superposition initially, left and right, cross, left and right. Because the reason why I'm asking is that we have super selection rules, for instance, coming from, let's say, QED, right? And then we cannot superimpose charges, different electrical charges in general. It could.
So these will be neutral, right? So the only forces are going to be gravitational.
Right. Right. I'm just talking analogy. So it could as well be that the sort of charge which is preserved, that quantum gravitational theory, could be the line element between two different particles, for instance, such that you wouldn't be able to superimpose those particles being across like different distances, because that would be violating the fact that the line element should be conserved under diffeomorphism. So in the same sense, I could expect that, in the same sense that I don't expect to superimpose electric charges because of superselection rules coming from the conserved currents of the gauge theory.
So this I don't understand. I mean, having an electron in a superposition of two positions seems like a perfectly normal.
No, I'm talking analogy. So I'm talking that the electric charge, which is conserved, impose a superselection rule that doesn't allow you to superimpose particles of different charges. Now, in analogy, it could as well be that the distance between different particles in a quantum gravity theory would be an invariant that would impose a superselection rule such that you wouldn't be able to superimpose different distances.
Again, so if I have an electron, there's no problem putting that through a beam splitter so that it's in a superposition of two positions. And I could have another electron that it's in the same superposition of two positions. And that's all that's going on here, except there's no charge.
Yeah, maybe I can come back to that later.
Right? I mean, we can have sort of, entangled electrons, right?
Yeah, sure, absolutely.
I mean, trivially, there can't be a super selection rule that just rules out superposition positions. I mean, that would deny their quantum mechanics. I can put a particle through a diffraction. I can see how you might have a mass super selection rule by analogy to a charge super selection rule, but that's not the cause result.
Right. Yeah.
So I just have two particles. Each one is is a superposition of two spatial packets. That's all that's kind of going on here. Okay, well we can come back if that's unsatisfying. But yeah. Okay. Well, that wasn't the thing I thought you were going to object to. I thought you were going to object to. Hold on. How did this show that gravity was quantum? Okay, so it's clearly something quantum's going on here, and gravity is involved, and it's. It's another one of the case, in David's paper he does sort of, refer to these experiments as well. I guess was kind enough not to mention them this morning so that they could talk about them. Right, it's definitely another case where we have gravity and quantum mechanics sort of involved in a new kind of case, but the way I've just presented it, all I assumed was, just a nice kind of Newtonian potential. I put a hat on the V and that's how I end up with this entanglement, and, I guess I put hats on the x's for the positions. Let's just leave it as an intuition. Part of the talk will be to sort of how people fill out that intuition. That doesn't look like gravity is quantum. That looks like the particles are quantum. So we need to sort of fill that. That's the question we need to sort of address first. Well, actually, it's the question we need to address second, because the question we're going to address first is this one about what this shows about semi-classical gravity. Okay, so David talked about this before. He wrote the equation slightly differently, but the Einstein-Müller-Rosenfeld equation, where you couple the Einstein tensor essentially to the stress energy tensor of matter, because the matter field is going to be quantum mechanical. And let's just think about what this theory predicts for the experiment. And so, does it predict that there'll be entanglement? So, I'll just throw this up. What actually happens? Well, if we have semi-classical gravity, we have to take the expectation value of the stress energy tensor. In this very simple case, when we take this, the expectation value of, of the stress energy tensor for GravCat1, that effectively means that we have, as in the Page and Geilker experiment, the expectation value of the mass distribution corresponds to a single GravCat located at position -d. Okay, so there we go, right there. The expected mass distribution for GravCat2 is a single, because it's, there's a 50% packet over here, a 50% packet over here. The expected mass distribution is a single GravCat at position d. So the potential that the left packet of GravCat1 sees in any position is just going to depend on the distance from the left packet to GravCat, this expected position of GravCat2, namely at d. And say the left packet of GravCat2, that's just going to be sitting in a potential that's due to a GravCat at position -d, that's GravCat1. The key thing is that, say, this term, anytime I have a left packet of GravCat1, it's going to be sitting in the same potential. Because I've taken the expectation value, it doesn't matter whether it's paired with the left packet of GravCat2 or the right packet of GravCat2. And the upshot of that is going to be, well, I've written all the potentials there, I've written it out, but I've told you enough to tell you, because the potential and so the phase that each term receives is independent of which of the terms of the other GravCat it's paired with, the whole thing's going to remain factorized. It's separable. The whole thing's still going to factorize. Okay, well, you can do the math, but once we take the expectation value, it doesn't matter whether we're talking about the left-left term or the left-right term. You can see what's happened. The potential that gets stuck on the left term of the GravCat1 in this term is the same as the potential that gets stuck on GravCat1 in this term, and the same for all the others. Since it's factorizable to start with, it remains factorizable. There's the factorization, so it's still a separable state. We don't get any entanglement if we have semi-classical gravity, precisely because we're taking the expectation value. All right. So one might say there's one sense in which we've witnessed the quantum nature of gravity. We've seen how things are quantum. It's not semi-classical. We've gone beyond semi-classical. But still, that seems like a fairly thin sense in which this might be a witness of the quantum nature of gravity. And I probably won't have time to talk about this, but I'll also point out, so people do present this as a sort of refutation of semi-classical gravity, and some other theories, sort of Penrose and Diossi theories, seem that they would be ruled out by this as well. But as far as I can tell, almost no theorists actually give any credence to those theories anyway. So this is a hard experiment to do, and so ruling out semi-classical gravity, it's hard to see how that's a full justification for the excitement of this experiment. So part of what's going on in the paper, and we can maybe talk about, is why this is a valuable experiment to do. Okay, so I'm now going to go back into the experiment. We looked at the naive model, just sort of stuck in a Newtonian potential in a sort of the way you would kind of do. I think if you were set this in an undergraduate quantum mechanics class. and think a bit more carefully about how we should really analyze what's happening in this experiment. So the first approach to this, which I will call the Newtonian model, actually gets us back to that point with the V with the hat on. Is that included in the messing around time? I hope not.
Somewhat today.
Okay, all right. I'll try to keep it up. Yeah, no. Well, we started a bit late as well.
Yeah, that's already fine.
Oh, gosh. Okay. It's all right. Okay. So, the place you want to start, of course, is with some more fundamental physics, so quantum field theory and general relativity. And so I'll give you a derivation of, how you might sort of try to compute this effect from more fundamental principles that's due to Anastopoulos and who actually are some of the protagonists here, although this paper isn't one of the ones that was sort of argumentative. Is that based on an hour, or is that based on 45 minutes?
50 minutes.
Okay, because I was giving people like an hour before I said that. All right, so then we're good. Then I feel better. But I'll, okay. That's what I gave you anyway. Okay. So, yeah. All right. Well, I'll find a good place to stop. So, right, so what do you do? So, how are we going to do this in more fundamental physics? I mean, it's pretty standard sort of physics. So we're going to start with general relativity. And let's suppose there's some scalar matter, because that's going to be the gravcats. So, well, to make things, tractable, we're going to linearize the theory in a Minkowski background. There's going to be gauge fixing that has to be done. And, you end up, if you do that, it's a standard procedure, then you end up with a Hamiltonian that looks like this. There's a Klein-Gordon part of the Hamiltonian that's describing the scalar matter. There is this Gaussian constraint term. Oh, you've got to be kidding me. Was this... Okay. Okay. You can sort of recognize that looks like is clearly a kind of a Newtonian potential, right? So epsilon is the matter is sort of matter density term. So we have sort of m squared on the top, and then I have a distance term, a 1 over r term underneath. Then so Tij is going to be the stress energy tensor. This gamma. There's a bar on it, but gamma ij, that's going to be metric perturbations that I pick up from linearizing in Minkowski spacetime. So the minus 4g term, right, that's an interaction between the stress energy and the metric perturbations. Ultimately, those are, these are going to be gravitational waves. These are going to be gravitons when we quantize. Then there's graviton-graviton self-interactions. And then, because it's perturbation theory, there's further kind of terms you can put in for higher order corrections. All right. But we just have these gravcats. In fact, it's going to be modeled that they are basically static. We're only kind of interested in the bit when they're sitting there, just sort of feeling the gravitational potential, which we're going to take is only affecting really the phase. They're not there long enough to actually start accelerating towards each other. So we just model it as these things sitting there. So almost all of this goes away. Okay? There's no sort of interaction between the gravcats. So there's no sort of, in the Klein-Gordon term, there's no interaction term between. There's no interaction term. There's no kinetic term because they're not moving. So that's going to drop out. And then, to do the approximation, everything's static. In fact, all the terms that have gammas in, the gravitons in, they drop out as well. And so, in fact, the only thing that actually is relevant for our experiment is this one term that's left here. Okay. Everything else can be neglected. And so, basically, we just get back to, when you quantize, you just get back to a Hamiltonian that's the Newtonian potential. And that's exactly the same as we got in the naive model that we just sort of, we just put in by hand. I mean, not surprisingly, of course, this is the derivation of why, starting from GR and quantum field theory, that's the right potential to put in. That is the right Hamiltonian for the static Newtonian situation. And then, of course, that just then feeds into the naive calculation that I did before, and gives us the term. So I think the things to be noted here, where is this term coming from? It's arising from a gauge constraint. It comes from gauge fixing the Hamiltonian, the full Hamiltonian, which I haven't written up there, that leads to this. And of course, it's fully determined by the matter distribution. All that actually kind of matters here is the epsilon that describes how matter is described is arranged in space. So if you think about this from a gauge theoretic point of view, the true degrees of freedom, right, the dynamics of this, once you've gauge fixed, all lie for the geometry, for the metric, all lie in the gamma ij terms. But they've all dropped out. They're not actually kind of relevant. So one attitude you get is, yeah, this is how we get to the naive approximation. It actually is fully justified by sort of deeper principles, and that's the right way to think of it. Moreover, there's no dynamics in here at all, so because the gravitons are not relevant to this effect, they're not going to be measured by the phases that are being predicted here. But surely if we want to see the quantum nature of gravity, we have to be seeing gravitons. So given all this, there's no quantum nature of gravity sort of here at all. That intuition that it was just boring old Newtonian gravity, quantum matter, but classical gravity is fully borne out by this analysis. Okay, I will come back to that. But at this point, so one way of thinking, you might have thought, yeah, that's exactly the right way to think about it. But there's another way of thinking about it where you think, but hold on, for the last 200 years, haven't we been painfully learning about fields? And didn't we, in particular, in general relativity, learn that the geometry is dynamical, it's really a field, things have to propagate causally, that Newtonian term is instantaneous, does not propagate causally. So isn't this all the wrong way? What we've just done really lead us to the wrong way of thinking about things, because what we've lost sight of is the fact that gravity is causal and propagates causally, and that's just not built into the model. And that's the lesson that we need to kind of represent in thinking about this experiment. Okay, well, sort of we can do it kind of think about that pretty naively. The upshot of what I'm saying, I kind of motivated it by talking about gravity being causal. But really what's going on is it's another dynamical system, and that's just not sort of been built into our model at all. And so really we need to start from scratch, describe the system not as a bipartite system with two gravcats and a potential in between them interacting. Okay? Instead there really are three systems here, and we need to kind of represent that explicitly. Namely, there's the two gravcats and there's a gravitational field between them. Right? So I don't just have a gravcat on the left and a gravcat on the left. There's also a third term in the middle, namely a state of the gravitational field in which they're sitting. This is GR after all. And so you should probably, or perhaps, okay, there's different ways you can think of what this sort of intermediate state of gravity represents. The way I'm going to talk about it here is it literally describes each one of these terms are eigenstates of the gravitational field. So they're kind of labeled by classical gravitational fields, all right? Or in particular classical relativistic geometries. That's what these labels are, and they describe if you're in that state. So eigenvalue, eigenvector link, well, you're in that's quantum state represents the corresponding classical general relativistic geometry. Okay, right, so that's what I just sort of said here. So for instance, these could be the geometries that you might be interested in are, here's the geometry it could be. This is the static Newtonian limit of general relativity. That's what the metric looks like. And those different gammas represent different ds squareds like this with different phi's depending on where the objects are organized, are laid out, where they're arranged. Okay. So this is exactly, I mentioned this paper before by Christodoulou and Ravelli. This is exactly the attitude that they take. They consider then the different geometries that arise. If you have a pair of gravcats both in their left positions, one on the left, one on the right, in particular the closest where number 1 is on the right and number 2 is on the left, so they're much closer. In each case, you have, gravcats at different distances apart, so you have different classical relativistic geometries when you solve this. Now, you sort of, the way the calculation is done, you now sort of think about each of those pairs as having an internal, its phase amounts to an internal clock due to its mass energy. They're now traveling through different geometries. There's going to be different proper times along the trajectories. You're going to pick up the same phase differences as we already predicted, except now it's going to look like a redshift. Okay, some of them just take more proper time to kind of go through to reach equivalent points. So you can predict it on this basis, and so now this very much looks like we have gravity as dynamical in here. And if you take this view, well then it seems, if that's what you think is happening in the experiment, then this really is witnessing a quantum superposition, because you can literally see the quantum superposition that's there. Each one of those terms has a different geometry, and that's the explanation. A couple of notes. I just motivated that by talking about causality and gravity being a field. Mike mostly did a nice calculation of this in the Newton-Cartan case. It's really that it's a third system and dynamical, a third system that has to be represented with a third slot in the tensor product space that's doing the work here. And you can motivate that by causality, but that's not essential. And then also this Burza paper, they don't think about the tripartite system in this way. They represent the gammas here are instead coherent states of the graviton field for them, and they get the same answer. Okay. So what's really kind of important is what I've said here is in this sort of analysis is that gravity the two gravcats don't interact directly. Each one interacts, as it were, with the gravitational field. There's no kind of direct interaction. You can think about it as gravcat 1 interacts with the gravitational field, and that effect is mediated by the gravitational field that then interacts with gravcat 2. And that's, when you've moved to the tripartite system, well, I used to say it's almost immediate. I've talked to some people recently who there seems to be some discussion about this, but there are theorems sort of in quantum information theory, in sort of extrapolations of quantum information theory to more general sorts of theories. Again, we have Marletto and Vedral, who are involved in this kind of work. But it's almost more or less a theorem that if you have two quantum systems that are unentangled, they can, and that they do not mutually interact, but only have their interactions mediated by a third subsystem. If that subsystem is classical, they can never become entangled. You can sort of see, if you think in quantum mechanics, you can sort of see that fairly easily, because if you try to represent the intermediate system sort of classically, I'll leave that. It's actually not too hard to sort of see. If you don't have, if the intermediate system doesn't have, it's quantum mechanics, so it can kind of only have sort of one variable, because it doesn't commute with anything else. So basically the way you'd make it was classical would be by not allowing the mediating system to have any non-commuting variables. And so it's kind of just stuck there. Nothing can actually really be transmitted. All right, sorry, it's not too hard to see, but maybe in 20 seconds of burbling, it doesn't help too much. Okay. So how long ago did you tell me it was 15 minutes? About 15 minutes? Okay.
You got a question?
Yeah, Dominic.
I don't quite see why you need to go to the tripartite model. Once you've got LOCC, local operation classical, you can't do entanglement. And the original, what you call the Newtonian model, if you measure entanglement, even with that model, you infer that field, which we can call Newtonian, must be in some way quantized. can't be classical because of the LOCC theory. So you can do that without the tripartite model.
So let me answer quickly. We can come happy to answer some more about that. So LOCC is exactly the kind of thing that they have in mind here. Well, I think the reply from the other side is going to be, in the Newtonian case, that just violates LOCC because there's a non-local interaction there, and so it doesn't apply. I think to apply your reasoning, you already have to kind of be thinking in the tripartite way. I really just have the two gravcats and they violate LOCC. Yeah. Okay. So this is the interpretation. I mean, now I'm feeling maybe it would have been better if I'd been dancing and singing. But
I think most of us have your slides.
yeah, okay, so maybe I'll just keep talking while he figures that out. So the slide I'm sort of talking about now is sort of a recap of what's going on. So I've given you the sort of derivations and I've kind of indicated how the interpretations go. I'm just going to make a few sort of interpretational kind of comments. So think about it from the Newtonian model point of view, and then so people who argue this way. So they're really going to say, what they want to conclude is the gravcats don't witness quantum gravity, or more precisely, if we observe entanglement of the gravcats, that isn't a witness of quantum gravity, because it's only that gauge fixed term that actually does any work. Okay? And that's really not quantum enough. On the other hand, in the tripartite model, well, clearly we are witnessing quantum gravity. I mean, just look at the state and you see we have a superposition of classical geometries, and what could be more kind of quantum than that? And indeed, the theorems tell us that's how, it has to be like that. So given these two ways of looking at things, the natural question is, well, which is like the right one? Does this show, which is the correct interpretation? Does this witness quantum gravity or not? And this is sort of the philosophical, the sort of meta-philosophical part of this, rather than engaging in the interpretation. Looking back at that, what we want to say is there's something kind of mistaken and wrong-headed about that question. Ultimately, what's the case is different people have different theoretical presuppositions, equally kind of reasonable. They don't share any presuppositions that would, in a sense, that would decide one way or the other, and depending what your starting point is, you can come to different conclusions. But there's no kind of shared view that will actually settle the two things. And really the question is, the question we're sort of dealing with is, how should you extract an approximate description of this, because this situation lies in the Newtonian regime, from more fundamental physics, and you can just be led to different points about the correct way to model. Okay, so the situation is theory-laden, and the best thing to do is just try to work out what the theoretical presuppositions are. Okay, well, I'm going to kind of rattle through that in a couple of slides, but I think it's worth saying it took us a year of kind of thinking quite hard about this to sort of really untangle what it is that different people were thinking. So, do a bit of reconstruction and then ask whether these things actually settle the debate, and from what I've said, you won't be surprised that the answer is no. Okay, so here's how the Newtonian argument could be put in the first place. So initially, this is more or less the way the argument was kind of put. Okay? The so-called true degrees of freedom, as we saw, don't play any role in the experiment. They're all the graviton ones. That's where the dynamics is. In gauge theory, we call those the true degrees of freedom, and they are not relevant to the experiment. That is true. Indeed, the whole effect is due to the Newtonian potential, which is a gauge constraint. There's a certain amount of sort of law of interpreting gauge theory that then, that says, then you're really not, these are the true degrees of freedom. If you're not seeing them, then that's really not a that's really not a real effect that's there. But that is actually, I think this sort of was the upshot of the kind of the discussion between people as well, that that's really not a very good argument, that this is sort of an equivocation on what it is to be a true degree of freedom here. And I guess the way, you can see that I'm putting it here is, although they're called the true degrees of freedom in standard interpretation, the question is, do they constitute gravity? Because we want to know whether gravity is is quantum here. And it's clear that just because they're called the true degrees of freedom doesn't mean that that's the whole physical content of the gravitational field. Okay, and then some arguments, so the arguments we're giving against that. Of course, what turned out to be gauge, what turned out to be a true degree of freedom, was dependent on the particular choice of gauge here. There are some things that are general across choices of gauge, but that things turned out to just involve a constraint is also an artifact of the gauge that we chose. Things could have gone differently. It also just can't strictly be true that there's no physics in the potential, because clearly different potentials represent physically different situations. Even though they're fully determined by the matter distribution, they're in fact instantaneous, they're non-causal, they clearly contain physics of the field. Different gravitational potentials have different physical effects, right? And indeed, if you really were going to push the line that only the true degrees of freedom, the graviton degrees of freedom, were gravity, then in fact all that stuff that Newton was doing, right, up until we actually discovered GR, there was no gravity, because that's all just in the gauge constraint. And that just seems insane kind of thing to say. So that really can't be right. Okay. So there's an equivocation, and there's a sort of tendentious argument going on there to say, to infer that from the fact that it's just the gauge constraint term, that we're not seeing some effect of gravity here. And I think those arguments were pretty much settled. So, still, when you look at the Newtonian analysis, it is still quite true that all that's doing the work is that Newtonian potential. We put a hat on the V, but that still doesn't seem terribly quantum. And it is true that it is kind of gauge. So, since we can model that way, isn't that the appropriate way to model it? And it seems right that if you pick the Newtonian way of modeling, then that is indeed not gravitational. Okay, let's just turn to the tripartite model. So, shouldn't we model gravity as a sort of intermediary? Perhaps motivate that by space-time causality. So, different ways people might resist this. So, one is, and I think that I owe this to Mike kind of in particular, so if you think that gravity should be described the way David was describing as an effective field theory for general relativity, then then you really are thinking, I think, in this case of the tripartite model in this case. But you might resist that. It seems very natural, and I think it's true that the vast majority of theorists in quantum gravity, do think that low energy quantum gravity, as David described it, is the right way to describe those regimes. But someone might be neutral on that and not want to kind of be committed to that in this case. And I think Mike in particular had in mind sort of experimentalists. They don't actually care too much about the theory behind what's happening. They're much more concerned in enough bits of theory and getting the experiment to work the experiment and just figuring out how to make the experiment work. So neutrality is sort of an option. There are people who actually have different kinds of views about how to combine quantum gravity, the quantum with gravity. And I mentioned, for instance, Penrose, and then there's other sorts of ideas people might have. As I say, for the theorists, that's much less common. But this is sort of the kind of key move I want to make. So look, even if you're a quantum gravity theorist who accepts a kind of effective field theory approach, low energy quantum gravity approach to general relativity, and as I say, that's by far, I think, the most common kind of understanding or expectation of physicists. I think you still might think that the Newtonian model, where you don't witness the quantum nature of gravity, is really the right way to go. All right. Sorry, I'm following through on my notes, but I skipped over one. I'm now the nevertheless one. So you might be fully committed to the idea that if you do the experiment, you will see entanglement, and that more fundamentally, there really is a quantum field here. It has the low energy quantum gravity description, so it actually, we have, that really, in some sense, there really are superpositions of gravity here. But the question is, how actually should we describe this experiment? What is the appropriate model for this experiment? And clearly that's a relevant experiment, right? If you think, in a way this is also part of David's talk, in some sense, really what's going on when you drop the pencil on the table is that there's a more fundamental, theory of quantum gravity that's describing. But we wouldn't use that to model it. We can just, we can treat the pencil as a rigid body if we want and just drop it down. And we don't actually have to, I guess it's the table that's solid. We don't actually have to bother with quantum mechanics to describe what's going to happen. We can do that and our model will not have to represent that. And that's really the kind of question here. And I think there's a very natural kind of attitude that the Newtonian model is really simpler. It involves less of the fewer of the technicalities of going further into quantum gravity, and so that really is the sort of appropriate model that we should be using here. So really, in some deep sense, when you see the entanglement, the gravitational field, of course, is entangled, and the quantum mechanical theorems tell us that. But that's not important. The way we should think about it and describe it is in terms of the Newtonian model, where we're not seeing anything quantum gravity. We're not seeing a superposition of gravitational states. Okay, so sort of three arguments for that view. So one is sort of a principle, you might say. If you have empirically equivalent models of some, you've approximated some phenomenon in two different ways and come up with two different models, well, the one that actually simplifies the most and involves the least fundamental physics is actually the better one, sort of a principle of simplicity. We do still have the fact that in the Newtonian model that the gravitational interaction is a gauge constraint, so in some sense we can model it in this sort of non-physical way. That sort of pushes you in that direction. And then I think another kind of argument, and I have in fact heard people give a sort of related argument to this. Look, I can tell you, it's not like I'm in denial about what the gravitational field could be in superposition. And indeed, I can tell you an experiment that would satisfy me, but it has to be more than the GravCAD experiment is giving me. And indeed, I've sort of have heard people kind of give that. So for instance, I might want to see the experiment that I said before, not the gravitational version of the photoelectric effect, but to have, for instance, have an entangled matter state that becomes decohered purely through interaction with the gravitational field, because then it would have to be entangled with gravitons, and that would sort of satisfy me that I saw the reaction, that I'd seen the quantum nature of gravity. Okay, I said me. I didn't mean me there, but that was playing devil's advocate. Okay. I do have another slide, but I will stop there because I don't know, kind of really have no idea where we are at this point on this thing.
Yes, Dominic.
I was wondering what in the analysis you've given is added by this to our understanding of the quantum nature of gravity over the Colella-Overhauser-Werner experiment, where we could in the interferometry over the Earth's gravitational field. Because I mean, to me, unless somehow the system is aware that there's a gravitational field caused by a microscopic particle, or even macroscopic, or perhaps, I know that in this case, entanglement is being caused. Unless somehow the gravitational field is aware of that, then it's going to be the exact same development of phase, the gravitational field causing.
Good. So let me just, I'll recap the experiment to make sure everybody knows the sort of cow experiment. So this was done in the 70s. You sort of fire a neutron, so you produce a neutron, you fire a neutron into an apparatus, into a beam splitter, which in fact could be oriented at different angles, but you imagine it sort of vertically, so right, one path of the neutron goes like that, and then recombines here, the other goes up and then across. So they now, because the Earth's gravitational field is here, this one is in a lower potential than this one, and so there's going to be a differential phase, and when you recombine, you see interference when it kind of comes out again. So in those, so we talk about that, in the paper, and there's also very nice experiments. But the difference is the source then is of the gravitational field is classical. It is the Earth. What's different here is the source in each case is quantum. So GravCat1 is sitting in the gravitational field of a particle that's itself in superposition. So, thinking in a tripartite way, there's a superposition of the field from this packet and from this packet. So that's the big difference kind of between them. Now the source is in a superposition as well as it were, the test particle.
And specifically in a coherent superposition, which is what distinguishes it from Page and Geilker.
Yes, yeah. Yes. Yeah, good.
So the other thing that I was curious about the initial states that you consider, it is a product state, right? And people have been questioning more and more the fact that when you have a constrained gauge theory for gravity, you cannot factorize it in space.
Yeah.
And so I wonder if you have any thoughts about that.
Yeah, so I don't. I mean, as you know, I kind of learned about this 3 weeks ago in London, and we sort of talked a little bit about that. Yeah, no, I think that's okay. So I think I really don't have much to say about that sort of formally. I think so. When you have a constraint, the general idea, right, is if you have a constrained gauge theory, it's not always clear that you really can write down systems as a tensor product of individual systems, as is sort of seems to be being assumed here. I mean, the other, so I think related, so I'm going to, I guess I don't have an intuition or an idea at all about whether this is sort of appropriate here, but I'm going to try and relate it to a particular sort of point of the talk. I think there are, when you relate this to the kind of theorems that Marletto and Vedral were proving, or I can't remember I've forgotten who the GGS is. The other, Flaminia Giacomini also is part of sort of proving these kinds of theorems. Although they're sort of generalizing, and I guess we give a sort of proof of how it looks in quantum mechanics. Again, you're sort of assuming the tensor product split as well between these things. And so I was talking to Marius Christodoulou, and I think he's kind of now worried about whether those theorems really apply sort of to this case, because it is indeed because it is a gauge field, and in various ways those theorems assume basically you have bits and qubits, so they're sort of discrete finite degrees of freedom systems, and that they're tensor products. So I think there's, I'm just going to kind of agree, there's sort of work to be done to show that if you have a more realistic sort of quantum representation, quantum description of the gravitational field, that the consequences of those theorems still apply. So, and I think also at the meeting, so Ravelli, I'm trying to think, I think one of his students gave a sort of one of the presentations was kind of work in this direction, trying to think about how to describe this better.
Because I guess one could make another argument which would be the fact that if you were modeling the experiment like that and you do predict precisely what happens, then that could be an indication of a departure of quantum GR, because quantum general relativity would prevent you of modeling the experiment with a tensor product structure. And so by doing that, maybe one could infer that somehow the constrained gauge structure of GR is not really present in quantum gravity. But I think,
I guess I was thinking the other way, that they'll be able to show that the tensor product assumptions are innocuous so that it does work out. But sure, there's a sort of modus ponens, modus tollens thing here.
David has a finger.
Yeah, I mean, I had to worry about the tensor product too, but it's not obvious to me it's necessary for the distinction to be drawn. I mean, don't introduce that second system at all. It's still the case that if I take my derivation from full quantum GR seriously, I've gauge fixed, and now I've got a gauge fixed observable for the gravitational metric. For the metric field. And now I can ask, is my total quantum state an eigenstate of the metric field? No, it's not. Are the components of my superposition eigenstates of the gravitational field? Yes, and they're enough. So if I'm taking the gravitational field aspect of my quantum gravity theory seriously, then I'm already entitled to describe that state L tensor R as being an eigenstate of the gravitational metric, which describes a certain spatial geometry, and I'm allowed to take this, RL or something as another eigenstate of the metric field describing different spatial geometry. I mean, it feels like that interpretive distinction doesn't rely on any essential way of introducing this extra, and I think technically formally suspect, additional Hilbert space factors. I mean, so take EM similarly. I'm doing electromagnetism and I'm in the electrostatic unit. It's still the case that the gauge fixed theory has electric and magnetic field operators, and it's still true that the state electron here is an eigenstate of the electric field operator with a different eigenvalue from the state electron here. And so the quantum state, if I'm taking the field representation seriously, that quantum state is a superposition of different electric fields, even though they're not dynamical.
Whether I write it as a tensor product.
Right, and I don't need to introduce an extra Hilbert space for, I don't need a tensor product, I don't need an extra Hilbert space for electromagnetic degrees of freedom to make it legit to say that's a superposition of electric fields. I just need the electric field operator.
Yeah, okay. I mean, that seems, this seems plausible. I think for that and for other reasons, I think it would be nice to see it worked out more carefully to make sure sort of understand really what's happening there. But yeah.
Emily has a finger.
Yeah, I was also going to say that, even in these constrained theories, you can still have well-defined tensor product structure relative to a reference frame. It will change as you move from one reference frame to another. But in this context, you do have a well-defined choice of reference frame because you're working in a lab and it defines the reference frame, and you know pretty well what the expected tensor product structure is relative to that reference frame. So could it not be the case that the description relative to the lab reference frame is enough to give you to justify the use of the tensor product structure, even if it might be a different structure from a different reference frame?
Can I take that as a sort of rhetorical question or statement of fact? Yeah, as I say, I think this is something I have not had time to sort of, think about. I mean, I think most people are optimistic that, right, for these kinds of reasons, it will work out. this would be sort of legitimate. But yeah. But I think it's definitely worth flagging that there's definitely a sort of simplification going, a big simplification going on here. Yeah.
David?
So, is there like a deflationary response to this available? I mean, you've cashed this out as like it's a substantive theoretical disagreement. Suppose I just want to say, you know, the word quantum gravity is up for grabs and you're welcome to mean different things for it. One set of these experiments tests a regime of quantum gravity in which gravitational degrees of freedom are frozen out. Another experiment tests a regime in which they're not frozen out. That's testing different regimes of theory. But, I mean, leaving aside the sociology of who wants to claim we tested quantum gravity to get a Nobel Prize, just terminologically, it's not clear to me what the substantive scientific issue is between, as to which one counts as a quantum gravity test.
Yeah, no, I think I basically agree with that, and I don't think it's terribly incompatible with anything we're sort of saying here.
No.
So I think related to that is one way of thinking it, and it sort of came up in some of the things I was sort of talking about. Different people have kind of different ideas of where the bar is to kind of call something quantum. So that's part of what's kind of going on here, and then there is a sort of just kind of terminological question about what you would sort of think was quantum. So I think that's kind of right. You know, there's a bit more going on here in the way I was sort of indicating, because I think there is a question here. People sort of think they're debating about what is the right way to model this situation that's sort of feeding into that kind of discussion and you know, producing different intuitions about where to draw the lines between classical and quantum. Yeah, I mean, you talked about the sociological sort of question here, but I mean, you know, I think it's that there is some sort of, that explains part of what's going on here and why this is sort of important. It will be a very hard experiment, a difficult and expensive experiment to do. So I think there's also some things are at stake, sort of other sort of pragmatic things like that. Actually getting this done. But yeah, I think there is also this sort of intellectual element, which has to do with what really are the most important sort of theoretical principles here. And I think I kind of wanted to bring that out as well. I mean, I guess I didn't get to the slide where I ended up calling the difference here as sort of a paradigm difference. I think that's kind of what the earlier discussion was sort of pointing at that ultimately we've kind of laid out the different theoretical presuppositions, and stepping outside, I think you can kind of see that both of these are pretty coherent sort of sets of assumptions and theoretical presuppositions that lead you to different points on this question, and that there's nothing really in the background that anyone could appeal to. Nothing that we've thought of, nothing that anyone's kind of actually come up in the debate to sort of sway people from one side or the other. So that's part of what we wanted to kind of highlight here as well. You know, the people in the debate are often then annoyed because you have to disagree with both sides, of course. And so depending on who you're talking with, you always have to pick the other, to try to convince them that their view isn't right. You have to kind of extol the virtues of the other view. And so each time you give the talk, you kind of end up arguing either way. But this also just seems to confirm our hypothesis, really, that this is kind of going on. So, yeah. So how are we doing? Are we kind of out of time, or?
Well, it depends on how we count. At 6, but we did start a little late and had the interruptions.
So that was an hour and a half so far, right?
Not quite, because we started late.
Yeah, okay. Well, I'm going to ask myself a question, and then I'll tell you a bit more. I know people probably want to go and get going because it's late, but I might just mention a little bit about the last slide, but I thought there was, David had another question. Sorry, Mark.
I find out, right?
So I kind of wanted to just kind of quickly come back to the question of, why do the experiment given sort of what I've said? Things seem kind of equivocal. Well, look, if you're on the sort of tripartite model, then, clearly this is going to show quantum gravity. It's going to witness the quantum nature of gravity. And so we should definitely do it because we want to see that and get our Nobel Prizes, and that, exactly that will be kind of great. And that seems that, I think, as I said, I've not said that either way of thinking is kind of wrong. That's a very legitimate, based on very legitimate theoretical principles, and I think that is the right kind of conclusion here. Of course, there's people who think, one should use the Newtonian model, and then don't think that we're going to get anything as exciting out of this experiment. But I think there's, in the paper, we try to develop a sort of third way of thinking about this that everyone should sort of be excited about. And, well, David, in your paper, you sort of talk about the different regimes for testing quantum, low-energy quantum gravity. I think so. What we instead appeal to a kind of thinking, a sort of Ian Hacking-esque sort of thinking about experiments that tries to decouple this from the theoretical questions and sort of questions of confirmation, and that what's really key is, part of scientific knowledge is the ability to intervene, to manipulate, to control different physical regimes, to actually build apparatus where we can actually control things. We can actually, in some sense, if you're going to go the whole sort of hacking route, make things real in the lab. And this, Dominic asked the question, this is exactly a really important new regime in the intersection of gravity and the quantum. Exactly the one where the sources of the gravitational field themselves are now quantum. It's not just sort of test particles in the field of a classical object, as in the cow experiment. We're in a new regime where we're actually looking at the gravitational field sourced by an object in quantum superposition, right? And that description is independent, of course, of either of these two models. This is going to be a sort of, just the very fact that it's a very hard experiment to perform means it really is a sort of technological step forwards. It really is a sort of experimental, advance. And for us, that, being able to actually manipulate that regime, taking it out of the purely theoretical into the concrete, the experimental, is itself a huge value for this experiment. And that, knowing how to do things and being able to do things is just as important as knowing, that things are true, what there is. So I think, part of the argument is to sort of emphasize that way of thinking about the value of this experiment. I think there may be other things to say about why this is an important experiment to do and why it sort of is exciting. As I said, ruling out semi-classical gravity, that in itself doesn't seem like a super exciting thing to do. I'd be interested if people have sort of thoughts on this, the Page and Geilker experiment and so on. And I've written about this, Chris has written about this. Physicists do seem very bothered about the possibility that semi-classical gravity is sort of a fundamental quantum theory. That's really all we're ever going to get in quantum gravity. But nobody actually thinks that. So if you think about it from a Bayesian point of view, proving, another experiment to show that, gravity isn't, semi-classical gravity isn't the whole story, it's just kind of quixotic because, maybe you're going to get a tiny bit of extra confirmation, but I think it's very, very little for people, and that's good. Physicists like to really pin things down. But I don't think it sort of fully justifies the amount of enthusiasm for this experiment.
David?
Yeah, I mean, just as an observation, inside philosophy of physics, I don't think that's true. I mean, we don't have the budget, but it's definitely true that in philosophy of physics, in the quantum gravity literature of the last 20 years, then semi-classical gravity has been taken really seriously. And I think wrongly, but it's been extensively defended by various people for, interested in
Well,
physical
Craig and,
So from
Craig
our
and me
point of
is
view-
sort of an example here. Yeah.
Yeah, from our point of view, it's really helpful for people to rule it out, because we collectively are taking it very seriously, even if the physicists themselves aren't, and therefore sociologically, there doesn't seem a good reason for them to do it.
Yeah. No, that's good. Yeah. I mean, I totally agree with that. Yeah, and I'm very much talking about why the physicists find it so kind of exciting. And I will note, and if they're
Just tell
physicists
them
want
something. We want to do it.
and I will also note a lot of these papers sort of seem to start with a lot of kind of, angstiness about, well, maybe it's just semi-classical gravity, maybe Penrose and Diosi are right. That seems to me out of proportion to how likely physicists actually think, or quantum theorists, quantum gravity theorists actually think that is. So I think there's still some kind of question that we've sort of been exploring and trying to open up about what the value of the experiment is that's sort of interesting. But yeah. No, I guess I can. Craig and I said there should be experiments of this. This would be great.
Any other questions or comments?
I can go on the rest of the language.
So please join me in thanking the speaker.